The main problem with HIV is that it integrates its genome into yours. Current antiviral treatments can suppress pretty much every stage of its life cycle, but the one thing the current treatments cannot do is remove the HIV genome from yours. The idea is to use CRISPR to do this, but there's a few problems. First of all, cas9 doesn't knock out genes by physically removing them, it knocks them out by abolishing function. Cas9 will create a double strand break at the target location, then non-homologous end joining will be used to repair this. This is an inaccurate process, so it's unlikely it will repair it correctly. If it does, cas9 will just cleave the DNA again. And the mutation that is most desired in this circumstance is a deletion causing a frame shift, which will abolish the function of the protein, effectively removing it even though it's still technically there. Cas9 isn't 100% accurate. If the guide RNA perfectly matches the target sequence, then it's fine. Cas9 will have a very high chance of cutting there. Let's say some other sequence somewhere else is one letter different from the guide RNA. Cas9 will still cut there, just with a reduced likelihood. This is where off-target effects come from, and as the differences increase between the guide RNA and the DNA, Cas9's likelihood of cutting there is going to decrease. This is a problem when using Cas9 on HIV, because the way Cas9 is going to deal with HIV is not by removing it, it's going to induce a bunch of mutations that will render HIV replication incompetent. But there is the occasional chance that Cas9 will cut the DNA, but the mutation will not make HIV replication incompetent. But either way, Cas9 will no longer recognize the target site as much because you've changed a few letters, and Cas9 will infrequently cut the DNA there. So what's going to happen is a thing called breakthrough replication. So this is a culture here of cells. Then let's apply the cas9 treatment, and most of the proviruses have been inactivated, except a few will be left behind because it's not 100% coverage. So there's going to be a low level of replication in the background, and then cas9 is going to keep on cleaving the HIV as it replicates, so it's going to inhibit it. But eventually what's going to happen is, if instead of cleaving the HIV DNA and deactivating HIV, what's going to happen is one of the proviruses is going to get one of those mutations where it's different enough that cas9 doesn't cut it very often, but it's still similar enough where the virus still works and it still spreads. And this is what breakthrough replication is, because now it's going to go through the culture unimpeded by cas9. Like, for example, if we target these non-conserved regions here, there will be plenty of deletion mutations found in the escaped viruses. This makes sense because these regions aren't entirely necessary and they're not fragile, so it doesn't matter if there's deletion mutations in them, the virus will be fine with this and it will escape readily. But if we target in conserved regions, such as these polycistronic regions, the escaped viruses, when you look at their genomes, you will see that they have primarily substitutions and the occasional insertion that preserves the frame, so only by 3 letters at a time. These are very rare because most of the times it's going to be deletions. The insertions and substitutions are rare, so viral escape will take a while, but it will still happen. So in order to make sure it never happens, to make sure there's no viral escape, you need to target multiple conserved regions simultaneously. Like in this study, they actually did successfully repress viral spread. They created like a graveyard of inactivated viruses in their cell culture's DNA. Another example of a treatment is developed by Excision Biotherapeutics, and you can see the cutting sites here. They're doing multiple. I do have a few problems with this, like these 2 cutting sites here and here. These are not conserved regions, so the virus is going to readily escape, like seen before. Another problem I have is, like, unlike what they claim, I doubt their virus is very likely to be excised. What's more likely to happen is that there's just going to be 2 mutations in the LTRs rather than the whole virus being excised, because non-homologous end joining is fast, so by the time the excised viral genome drifts away, it's just going to get repaired and it's just going to still remain integrated. This very unlikely. And they have also they've taken this treatment into the first ever human trial of CRISPR against HIV. The trial didn't work when the patients were taken off their viral repressing drugs. The virus rebounded. One patient did have a delayed viral rebound, but for the most part it failed. The good news is that there were no off-target effects, which was the main point of this trial, since the main trial's purpose was just test safety.